All right. Well, good afternoon, everyone. Welcome to our feature talk today. My name is Trevor Grove. I'm a volunteer with the museum. It's been claimed, however, that I'm actually an artifact of the museum. I just don't have a barcode on my forehead. Sorry. Our speaker today is Steve McDowell. Steve joined the university's computer systems group as a co-op student in 1977, and he was one of the 3 co-authors of the Waterloo microAPL that we're going to look at today. Eventually migrated to Watcom in 1981, where he stayed as a developer for the rest of his career. Graduated from math here 1982 with a bachelor's on the Dean's Honors List, and eventually retired. The company by that point was called SAP, but as Steve pointed out, he remained a CSG Watcomer at heart. So, Steve, take it away. Thank you.
Thank you, Trevor. Thank you, everybody, for coming out. Just before I get started, I was going to say it's a little cold here, but that's a bit of a lie. I feel I have to put this on. We'll probably have to take it off too. Thank you for coming. As Trevor says, I was one of the developers of Waterloo microAPL, and when I was asked to do this talk, I thought about it for about a half a second and said yes, because I feel I've had a story to tell for a long time, and it's not exactly dinner table conversation. So this seemed like an opportunity to get these things off my chest. And if the demo demons are good to me today, I'm going to do a little bit of a live demo. I do have a backup plan if that doesn't work so well. So a little bit about me very briefly. For me, computing started at 14 years old in Ottawa in 1973, using, these are called Mark Sense cards, which you had to fill in with a pencil and hand in to the teacher, and a week later you get your printout, which would be pages of syntax errors, which you would then correct, rinse and repeat. Maybe 2 months later, you get your assignment done. Not an auspicious start for a career, but it was interesting. But then somebody told me about Carleton University, that they had a place where you could go and key punch your programs and hand them in and get the results back minutes later. So I became a bus rider, went out to the university. A couple of hours later, my assignment was done, I handed it in. I'm not sure what I did for the other 7 weeks, but it started to look a little bit more like an interesting career. Then for good or bad, there's good sides and bad sides. My father was in the military, retired. We moved from Ottawa to London after grade 10 for me. And I went to this beautiful high school here, Saunders Secondary. And again, incredibly good luck. My homeroom happened to be in a classroom that had this weird wall of glass along one side and the back, an elevated floor, a guy walking around in there doing some mysterious thing, which I had to go and investigate. And of course, the school had its own computer, which was mind-blowing. I was an older one even back in the day. It was a Honeywell GE115. I found these images here of the GE115, and it's a pretty close approximation. We didn't have quite the fancy wardrobe that this young woman is wearing here, but she's standing in front of the twin 2 megabyte, 5 platter hard drives. Wow. 2 megabytes each. One was the operating system and one was the storage. The gentleman on his right is the card reader, the printer's on his left, and the computer itself is in the background. And I was very fortunate. I got interested right away, and with a couple of friends, we got to know the teacher and volunteered, and we started operating the computer. Eventually, kind of kicked the teacher out and really operated the computer. And that's really where my interest in computers blossomed. I learned COBOL there on my own, and couldn't do much with COBOL, so I learned assembler, and I wrote invented my own computer language, wrote a compiler to compile that language, and it was just something to do. But we were there early in the morning, we were there after school at night. We ran the attendance, which was done through punch cards, and we even spent our summers. I don't know why this is timing out so fast. Anyway, and while I was there, I learned about the University of Waterloo computing program and the co-op program, and I was like, well, that's where I've got to go. So in the fall of '77, I came to Waterloo, and my very first semester, the computer class that I took, Wes Graham was my prof, and I think most of you know who Wes Graham is, a pretty the major figure in computing here at Waterloo. So it was interesting to at least know who he was. And for those of you who were here, Widget was the system that we were using here. So I'd gone to key punches with minutes of turnaround to terminals where you type in your program, you type run, and then you wait, because what the system's doing in the back end is taking the program, submitting it to a mainframe, running it, and then you get the result back. And in my memory, maybe the numbers have changed, but it's about 45 minutes of watching the queue number descend. And from 45 down to 1, and then you get a result, and then so my memory is the next revision is even better, because you started at number 25, you get down to 1, and then you go back to 25 because there were 2 queues. Anyway, it's what it was. I actually did go and find a place in the building where I could run a key punch and print out. I actually went back to the old cafeteria style running jobs there. But for my third work term, I was applying for a new position, and again, great luck. Didn't really feel great about the options that were available to me through the normal round of interviews. Went to the late postings board, and there was a listing for the computer systems group. Don't really remember what it said, but it sounded kind of interesting, so I applied. I went to the interview. Eric Mackey was one of the interviewers. I can't remember who the other one was. But the interview was going very well, and we talked about what CSG was doing at the time, and they were writing a compiler, I think, for structured basic. And I said, oh, Water wrote a compiler in high school. And they, what? That's not in your resume. Perhaps it ought to. But anyway, I think that clinched the deal, and I got to start a computer systems group in the fall of 1979. At the time, just a little history, the computer systems group was located in this building. It was colloquially called the Bank. And the reason for that, it was an old Bank of Montreal. Before my time, it was an active Bank of Montreal, the computer systems group. I believe they were upstairs. And in the daytime, it was a bank, and at nighttime, people were hanging out, and I guess that led to some interesting visits from the Waterloo Regional Police, wondering why the lights were on at 3 o'clock in the morning in the bank. By the time I got there, CSG had the whole building, and that's where I spent my first, I guess, my 5 or 4 work terms. And this collection of people are my colleagues. Unfortunately, I'm not in that picture because I'm the one taking the picture, and I forgot that I had a timer. But, so I'm just going to say, so CSG's task, I guess, at the time, from my perspective, was they were to do research and development into the use of computers in education, how to teach students how to use computers and how to think properly for computers. And so they were unfortunately responsible for widgets, for good and many other things. And I've said many times to many different people, I feel very lucky in my timing getting into this career because when I came to CSG fall of '79, microcomputers were a thing, but they weren't really much more than a hobbyist toy. But CSG was looking at how to use microcomputers to teach computing, to get students off the mainframes, I think was kind of the main thing, but also to increase turnaround or decrease turnaround time. So they started on a project. There was a Commodore PET, which I remember playing Space Invaders. I don't know, Dave, did you do that too? And they were experimenting with that. It was not practical for what they ultimately wanted to do. But some wizard figured out that if you did certain engineering things that are beyond outside my pay grade, they could turn the Commodore PET into the Super PET with an upgraded processor, more memory, and enough horsepower to get the job done. And as part of that, it was improving the languages that were being used. So Waterloo Structured Basic was about teaching students how to program in BASIC, but they wanted to take that concept of of a user-friendly or programmer-friendly environment where if something goes wrong in the program while you're compiling it or while you're running it or whatever, you don't just get Fortran error 416, which is what I got in my high school Fortran. You get a nice friendly error message So there were two computers that sort of came out of that around that time, and they're very, very similar, almost identical internally. So the one in the middle is called the microWAP. It's a Motorola 6809 16-bit processor. The one on the left, as we see here, of course, is the Commodore SuperPet. And to borrow from Trevor's talk, the microWAP is like a headless or monitorless SuperPet. So it's basically the same machine. And forgive me, I'm not an engineer, so I'm glossing over perhaps some details. And I will give credit also back to fellows up in the right-hand corner there, Jerry Christ. He was working, sort of doing the engineering level work, I think, for CSG, and responsible for a lot of things, but I believe he ultimately built the microWAP, and Jerry went on to found Northern Digital, which is a company still in operation here in Waterloo. So I'm not going to go into a lot of detail on this slide, but I kind of wanted to draw this thing. What makes this structure unique, at least in my worldview, it's only a 16-bit processor, which means 64K memory, and still, how can you do some of these languages in 64K? Well, the trick was the main processor is data 64K. The processor sees 64K, but there's a 4K bank in the middle that they map in and out all kinds of different 4K chunks of memory. So each language, I think originally it was APL, BASIC, Fortran, and Pascal. I think COBOL came along a little bit later. Each language can have up to 16 of these banks when it was running. So in APL terms, when I say it was a 64K APL, well, it was sort of 64K that way and 64K that way. And it was quite a clever structure to be able to operate in that environment to get these programs running. So if you've been over to one of these computers, this is when you boot up the computer Commodore PET, SuperPet. This is the list you get. And if you select APL, this is what you see. And I have to tell you, when I saw this 2 weeks ago, it just blew me away because the last time I saw this was 40 years ago. So this is the Waterloo microAPL. That was the first version, running on an emulated Commodore SuperPet on this laptop. I'm going to try and do lined up. So, first question for me anyway was, what the heck is APL? I've never heard of it before. And a little bit of research shows that it stands for programming language, and that's not very exciting. I think what happened was that the gentleman who invented APL, Ken Iverson, wrote a paper, didn't have a name for it, he just described it as a programming language, and that's stuff. I think of it as an array programming language. That's what it does, array processing. Some of the things it's known for, just in general, got a weird character set. People write one-line programs. That's just an example I scraped off the internet somewhere. I don't even know what it does. But there's a theory that with APL, every program that could be written in APL could be written in one line. And you can imagine it didn't take long before the next line appeared, which is the write-only language, that people would write these programs and somebody else trying to figure them out would just be, what. And because of the weird character set, the other expression was, it's all Greek to me. And the reason for that is this character set, it's a little bit hard to see, but it's a mixture of just the uppercase letters, English letters, some Greek letters, mathematical symbols, and then a bunch of what I just call made-up symbols. And over here in the yellow, that's somebody else's product, but it's the same keyboard layout. You can see a lot of the symbols. One of the things that makes this keyboard challenging to use is some of the symbols that are in APL and in a normal QWERTY keyboard, they move. So the equal sign, which is usually over here somewhere, is up above the 5. The square brackets and other things all move. So it's a bit of an adventure typing on a QWERTY keyboard for the APL character set. Most of the time, like over here, you'll see stickers. I challenge myself, I don't have the stickers on here. I do have a little map if I get lost. But even all of those symbols were not enough for what Ken Emerson had in mind. All of the functions and operators in APL that he had in mind, he needed more symbols than that. And that leads to this little box down in the corner here, I don't know if you can read, but it's called overstruck characters. So he would form a new character, for example, maybe one of the ones you can see more easily. This is a circle with a backslash through it. So you would type, here we go. You would type the circle, backspace, and then the backslash, and it would combine those two into an overstruck character. And in the real world, this was done a couple of ways. In the bottom left corner, you see, I call it a selector type ball, but over here we have an IDM terminal. The little type ball that spun around and did things. They just took that type ball off, put an APL one on, and away you go. The keyboard in the middle, if you look closely, the shifted characters, there's a red one and a black one on some of the keys. The red one is the APL. And then the top right corner, this is actually from my involvement with APL, Waterloo microAPL, eventually became Waterloo APL. And we provided, along with APL, you got these transparent stickers that you can put on your, in this case, IBM PC keyboard to help you find the character you're looking for. So this is, I had fun typing this one out because I wanted to show all of the symbols that actually perform a function in APL. And to be honest, isn't all of them. I had to cheat on the third line there. But the first line is 29 symbols. Each one of those symbols is just a simple one-stroke key on the APL keyboard. And each one of those symbols will take either one or two operands rather, and produce a result. And those operands are arrays, which we'll get to. The second row, I list all of the overstruck characters, so there's 14 of those. So a total of 43 symbols, some with one operand form, some with two. So there's a lot of different functionality built in. And if that's not enough, there are operators on the third row. I just put some examples there. They take two functions as parameters and then perform a more complex function with that. So the bottom left one is inner product, so plus dot times, so you multiply all the array elements and then add up the results. The next one over is outer product. And then the one that's probably used most often is plus slash, but you can use any of the arithmetic operators there. It just says, go along one axis of this array and apply this function between all of the values in that array. So plus slash, a vector, gives you the total of all of the elements in that vector. So some of the operations are very simple, some of them very complex. I'm going to attempt to demo demons here. So I said that the APL is all about arrays. Get this into full screen mode. There we go. So first of all, I thought I'd just type this. Oops. Demo demon get me? No. Oh, caps lock is on. Caps lock is not your friend in APL. Right. So that is quad WA. That's the work area. That's 28,715 bytes. That's my play space here. It's not very big. My phone has 4 million times as much. Anyway, so the simplest array, I suppose, would be the vector. You can enter them different ways. So in this case, I just type a bunch of numbers and it formats as a one-dimensional vector. I cheated on the first one by putting iota 5. That's one of the first functions that everybody learns, and it generates the first 10 numbers. Multi-dimensional arrays, you can't type them in directly on the keyboard, so you have to type them by creating them from other things. So if I want to make, I'll explain this in a moment here. So you've seen iota 5 generated 5 numbers, so iota 12 generates 12 numbers, didn't need that many. The little p is the character row, And this, if I use the word monadic and dyadic, monadic means one operand, dyadic means two, it's just an APL thing. And the dyadic form row means reshape. So on the right-hand side is reshape what? On the left-hand side is what are the dimensions of the thing that you want to reshape. So it creates a 2x3, 2-row, 3-column array out of, well, I made a vector of 12, but I didn't care, I just threw away the extra elements. You can do higher dimensional arrays if you want to, just for fun and to challenge myself on the keyboard here. This thing keep going away. Yeah, that's the demo demon I've got, I guess.
Yeah,
The screen's just gonna.
Is it getting power?
That's what I'm wondering, if it's maybe losing power. Check the there. Well, it says the battery's full. No demos completely, but demo demons getting involved. So make this more interesting. All right, so here I made a 3-dimensional array, so it just basically takes the 2 dimensions and prints each plane of them one after the other with the space. So what I'm doing here, generating numbers 1 to 100. The upward arrow is called take. And what it does is from an edge of an array, it takes a number of elements in from that edge. And if I had said 24 take, it would have taken the first 24, which is no fun. So I said minus 24. I'll explain that in a moment. So it takes the last 4 elements, 24 elements of the numbers 1 to 100, and then reshapes it into a 2x3x4 array. And then a funny little elevated minus sign in front of the 24 is another unique thing about APL. Unlike other programming languages where you just use the minus sign. Minus sign is an operator that get as a function will get confusing very quickly, so they created their own special minus sign symbol called overbar or negative. So I survived that one. Now, one of the things you might notice, or maybe you haven't, but one of the things that's very unusual about APL is the order of operations. By definition, APL operates from right to left, which is counterintuitive for most people. Most programming languages go the other way. But if I type 3 plus 4 times 5, it gets the result you would expect in any language. But if I type 4 times 5 plus 3, any guesses?
32.
That's right. So there is no hierarchy. Because with 43 symbols and all the variations and stuff, a hierarchy would be a nightmare. So it is simply right to left. And once you get used to it, it actually makes a lot of sense because each step is 4 times everything that comes after me. That's what was going on. It's 2, 3, 4 reshape, whatever's to the right, minus 24 take, whatever's to the right. And it starts to make sense. So in this case, it does 5 plus 3 first, and then multiplies with 4. I'm sure I'm taking the demo. I'll just go over this one quickly. So IOTA generates the numbers 1 to 10. If you come from a background or the program you're working on, the application you're working on, it makes more sense to think of arrays starting with element 0 instead of element 1. There's this thing called quad IO. You can set that to 0 and all of a sudden base 1 becomes base 0 and everything continues on. Now mind you, things get interesting if you forget what quad IO is. The other thing that I find really interesting in APL, and I did want to talk about this from a bit, is the concept of what is equal. APL implements something called fuzzy equality. And under the covers, our implementation of APL, all numbers were floating point numbers. We did not implement anything in integer. So, as you know, with floating point numbers, things get approximate fairly quickly, and then you have to be careful. So in this example here, first line, 3 star 2, that's not the times operator, that's the power operator in APL, so that's 3 squared. And it says that the answer is 9. In the second line there, I say, well, what is 9 minus 3 to the power 2? Well, that's not 0, it's just so 3 to the power 2 is not quite 9. But if on the third line I say, is 9 equal to, and that equal is it equal to, not a sign, in other languages, is 9 equal to 3 times 2? It says yes. So that is comparison tolerance. So this variable in the middle of the screen, CT, is basically this fuzzy equal concept. So you're comparing two things, it gives you a little bit of tolerance for equality. And if I set it to 0, and then ask the same question, is 9 equal to 3 to the power 2, the answer is no. Hey, come on, not intuitive? So in the live demo, as you can see here, you can see that I'm working on an extremely live workspace. The screen is just a screen. You can cursor around, you can change things. Whatever line the cursor's on, you press enter, the return key, it executes that line. And that could be useful for a lot of things. You can do very complex APL statements and operations in that environment. But of course, eventually you probably want to write the equivalent of a program, which in APL are functions. So I did not want you to sit there and watch me type this one in particular. So at the very top there, we have the upside down triangle. It's called del. And that begins the definition of a function. In this case, the function is called calc. And it takes a single argument, which is a, and kind of boring, but it does the sum of a, and then an average of a, and then it prints it all out. So you can see here, I'll stand up for this one a little bit. All right, so we have this plus slash operator, so we're going to assume A is a vector. You could put in an array if you wanted to. It would just be harder to lose the result. So the vector term plus slash A just gives you the sum of all the elements. The average is going to be the sum divided by the number of elements in A. So you remember row or reshape was something that took the dimensions of an array and another array and reshaped it. Well, row by itself on an array just gives you the dimensions of the array. So the shape of A, that's the word we use, the shape of A is the number of elements in the array. So that'll just sum them up. Average is the sum divided by the number of elements. And then we want to print them out, and I mentioned APL has all the numbers are floating point, it also has characters. So check the...
It's just your screensaver.
Just use what? Yeah, a couple more functions I threw in here. So I want to print the text sum colon followed by the sum. Well, these are characters, these are numbers. APL doesn't let you mix them together, at least our version of APL. These ones it did. So there's this funny little operator here. This is one of the overstruck symbol. The colloquial name is thorn. It's an upside down T overstruck with a little tiny circle. And its job is to take a numeric array and turn it into a character. And then a comma is catenate. So if you have two vectors, A comma B, it just takes all the elements of A followed by all the elements of B. So all this is doing is producing a character array, in which you're not doing anything with, so it writes into the screen. And so there are the results right there. So there's a couple of system fans. You can see what's in your workspace. And these things just accumulate over time. Eventually you get a wistful, which tells you your 28,000 bytes are all used. But you can save your workspace and load it back at other times. I'm not trying to do this environment. So the project itself, so I did Waterloo structured basic for a bit, and then these languages are starting up. And I, along with another quant student in the same stream as me, Gino Koski, were assigned to APL. And once we figured out what APL was, off we went. And even though the project was probably managed by, I'm going to guess Ian McPhee was the main guy at the top of that. Ian didn't know APL, but John Wilson did. So John was upstairs in the engineering department. Apparently, Trevor tells me he had a PhD in combinatorics and obviously had a background in APL because he really did know this stuff inside out. And anyway, Gio and I, we co-developed APL. I did the built-in functions, which is mostly what I'm talking about today, because that's what I'm familiar with. Gino did everything else, all the management, the function definitions, the file system, and everything else. So we'd be running along and say, okay, I need to add 2 things, and call Michael. And I worked with Gino right up till 2010. Unfortunately, Gino passed away in 2010. But he and I, like me, he stayed with the company right through his career. So coding the built-in functions, we were using Waterloo systems language, which may have come up in some other contexts. It was kind of like C. I actually liked it better than C. When we moved to C, it was kind of a step in the wrong direction. It had a little bit more structured programming stuff in it that I found very useful. But it was designed for portability. It was my first exposure to it. I think it's probably being developed now already. But John Wilson was the one who knew what all these functions had to do, and he would show up sometimes a couple times a day, several times a week with a piece of paper in hand, and he would give it to me, and it'd be covered in APL, and this is the algorithm for the function that you need to do next. And sort of look at it, okay. And my job was to turn that into functioning code that could be compiled by Whistle and executed in this environment, and to fit all these functions and all the stuff that Gino's doing. We had to fit all this into 16 4K bags. I still can't believe that was even possible. So for the most part, that went fairly straightforward. A lot of the functions have some complexity to them. Some of them are pretty straightforward. I didn't really need an algorithm for iota 5. But the whole time we were doing this, there was a function lurking at the end. I'm going to need a sip of water before I do this one. There was one that I was kind of dreading coming because I knew it was going to be the last one. It was going to be the hardest one. And for those of you who know what it is, I think I hear some chuckles in the room already. This is a symbol for the function, quad divide. It's made up of the box symbol and the divide symbol. The box is often called divide. Also got the colloquial name domino. And what it does is matrix division. Now I will confess to this room, I did not know then what matrix division meant, and I do not know now. But I had to implement it. And as part of this talk, I did a little bit of research, and I mean, I do have a little bit of understanding. I haven't been math after it. But it does least squares, trend lines, and curve fitting. Sure. But John came down with a page full of APL, and was like, oh, geez. And it was time to get on with it. I had one 4K bang left, and it had to fit into that. So I'm telling the story because to me it's a high point, and to some extent it can be a low point in my career. But I spent 3 days decoding this. And I have to understand what the algorithm does, but I also don't implement it the way he's written it because it would be very efficient to do things literally as the APL statements say. So I'm trying to understand the way you're going through the arrays and processing them and how to optimize that, because I also have to fit it into the space. And spent 3 days of probably the most intense studying and coding and everything else, and then finally writing the Whistle code, compiling it, getting all the compiler errors out of it. And finally, after about 3 days, it was time to run it for the first time, and I typed in an expression, and sort of, you kind of have the computer at an arm's length because you don't know what it's going to do. And to my absolute astonishment, it produced a result. And so my first thought was, can't be the right result. And so I did the inverse operation, and I got, like any good division operation, if you do A divided by B, you get C. If you multiply C by B, hopefully you get A. And I did. And I was like, holy cow, it works. And probably said something slightly more forceful than that. But I told Gino and some of my colleagues, and eventually I went upstairs and told John, and he came down and I showed him, oh, that's really good. And he went to Ian, and Ian went to Wes. And Wes wasn't around a lot, and he was a bit of a scary figure. Not really a scary to talk to figure, but he was, up there. And so I give him the demo, and everything works great. And then he says, can I try it? I didn't know what that meant. Because, the funny thing was, I had to use arrays A and B, and he just typed A divided by A. What could possibly go wrong? Well, it should be the identity matrix, but it wasn't. And I kind of slumped off into the corner of the room, feeling kind of embarrassed. And I was told that was just a Wes thing, that he could find the edge cases on things all the time and not to worry about it. So fortunately, I fairly quickly figured out what I'd done wrong and fixed it up. APL was done, and we started sending it out to people to use. And from Trevor's talk and other, I know that the Super Pet did get used at the university, I mean, McDowell. But around the time that was starting to happen, the game changer arrived, which was the IBM finally released their much anticipated PC. And I think the writing was fairly quickly on the wall that the university was going to go to the PC. And well, we had this Waterloo systems language and portable language environment, so we started porting APL to the IBM PC. And somewhere around that time, I remember I was working in the basement of the bank, and somebody came into the room and said, "You're not working for CSG anymore. What? You're working for this Waterloo Computing Systems Limited, this company that's just been created." And Ian McPhee, that I mentioned earlier, he sort of created Watcom, short form Watcom. He and some other people did, and the decision was made to take the microlanguage project out of CSG and allow Watcom to commercialize it. So I got traded without discussion for along with APL and Geno and all the other languages and all the other developers related to the languages to Watcom. Now, my day-to-day didn't change. I continued working in the bank until some space opened up down the street. But that's how I ended up in Watcom, and the languages got renamed at that point from Waterloo microAPL in our case to Watcom APL. Now, I'm going to go over this really quickly, just for the younger people in the room. The development environment in those days, like you guys have it so easy nowadays. we were compiling and editing and compiling on a mainframe computer, and when you were done, you compile your modules, link them together, you get an executable, you download it in binary form to the PC and run it, it would explode, and then you would use the native debug facility, which was assembler based, no source code, no variables, no nothing. You just had to know how things moved around and understand how the program was working. But builds character, they say. And I think Control-Alt-Delete was probably our friend a lot of days. I understand we ported APL to IBM VM-CMS, and I may have even done that myself, but I have no memory of the project. I think it was probably to demonstrate portability, and we did. I don't think there was a lot of commercial use for that. We were really focusing on the smaller environment. And then the next step, or final real step for APL in terms of Watcom, was in the early 80s, the Ontario government Ministry of Education decided computing was important, that was good, and decided to standardize on the computer that was being used in education in Ontario. And out of that popped this Semcor icon. Semcor still exists, I Googled it, and they still exist, I don't know what they do now, but at the time they created this. And what was nice about it from our perspective was it was 8086 based, the same as the PC, so it was not a difficult one to do. The operating system was different, it wasn't DOS, it was a Unix operating system, which back then it was just a real-time operating system, Unix-based. Nowadays it's more well known for being part of BlackBerry and probably running behind the dash of a relatively recent car. Has a trackball instead of a mouse, because those damn students would probably pull the mouse off. And they were networked. There was a file server that would run somewhere. And I remember when we got our first one, it was a box about this big and it had a 10 megabyte hard drive. We stood and stared at that thing for hours going, wasn't that great? And Watcom languages, Ian got involved with that, and we got the languages as part of that system. So I started working on that for a while. Fun the trivia I picked up while I was researching this, the nickname for this that I'd forgotten was the Bionic Beaver. So that was kind of it for APL in terms of my involvement as a developer, like developing APL. I used it mostly for testing, but there was one time I was here. One of the nice things about being here at the Computer Systems Group was that I could take courses while I was working, and I could work while I was taking courses. So I was, for the rest of my time at Waterloo, I was doing both. And one term I was taking, I think it was the operating systems course. And I had to do an assignment that showed real-time processing and stuff like that. And I was also supposed to be writing test cases for APL. So I went to the prof and I said, can I write this project in APL? Write a little kernel in APL and we'll execute functions in APL. And sure. So I actually got to do my project at work and get paid for it. And then we got a decent mark. Maybe the prof had no idea what I was showing. It worked there. The only reason I leave this slide up here was some conferences we went to. One, John Wilson, Gino, and I went down to Blue Mountain Lake, New York. We were wakened at 6 o'clock in the morning one day by a 5.3 magnitude earthquake that turned out to be absolutely directly below us. And being 1983 and Ronald Reagan and the evil empire, I thought World War III had started. But once we calmed down, we just felt that the earth had moved for us. I did have a little time on the APL Standards Committee. I think I went to 2 or 3 meetings. But APL was moving on way beyond what we were doing at this point. IBM had already released APL 2. IB Sharp was the other big player. They had a competing APL that, what APL 2 introduced was the concept of nested arrays. So our arrays, an array contained elements that were either characters or numbers. I mean, they're all the same in an array. APL 2 introduced the concept of arrays that each element itself could be a character or a number or another array. And within that array, more arrays. So you could have arbitrarily nested arrays to however many levels. And it was pretty clear to me we were not going there. So I attended 2 or 3 of these conferences, but they didn't really take us that seriously because we weren't really able to talk at that level. But it was interesting. And I know there's one fellow over there I'm going to talk to afterwards. I did want to say anybody here who has a lot of experience with APL, I would like to talk to you, because while I know APL and I used APL, I developed it mostly. I didn't develop with it, so I'm not an expert. Especially hearing, as this fellow tells me over here, that APL is still used today in some places. So just some random thoughts I wanted to put in here. I did discover towards the end of, this is probably mid-80s by then, it was really winding down. When I first started using APL, I'd come from the standard programming environment where an array was something you wrote a loop to go through. And it was hard to get beyond that, even though APL was all about these functions that could do those things for you. It's still hard to break that paradigm that's been in your head for a long time. So about 2 years in, though, I realized I was starting to think about a project, and I was envisioning in my head an array and spinning it around and stretching it and correcting it. Oh, this is why this light just. So I thought that was interesting. And until 2 weeks ago, my final chapter would have been 2014. I was still working at SAP, and I got a phone call from the receptionist saying, "There's a guy down here who wants to talk to somebody about Waterloo APL." And I was like, first of all, how did they know it was me to call? And but I went downstairs and met the fellow in the lobby, and he pulls out his Android device, which is running an emulator of an IBM PC, which is running Waterloo APL with character set and everything on it. And he showed it to me, and it was really fascinating to see, because at that time it would be 30 years since I'd laid eyes on it. And he wanted help to figure out how to distribute the thing, and I said I wasn't able to help him at that time. Apparently, God, you figured out how to do that. I was fine by the time. Anyway, and then my final random thought is I am so excited to know that I have this environment that I demonstrated. I have this on my laptop at home from the shop. I now have APL at home. I am going to play. So conclusion, I wanted to use this talk as an opportunity to say thank you to specific people, thank you to the opportunities I've had in my life. My career has been fantastic. Met Jim Stewart at Saunders Secondary School. I couldn't find a picture of him, unfortunately, but he was a huge influence. University of Waterloo, Computer Systems Group, of course, and Watcom, and the people I've talked about, Wes, Ian, John, Russell, and Gino. And for today, I specifically thank you to Trevor Grove for assisting me, Josh in the back there from the Computers Museum who is helping with the technology here, and Scott Campbell as well from the Computers Museum. Thank you everybody for listening.
So before you leave, are there questions? I'm betting. Somebody must have a question.
Softballs, please. If not, I'm planning to stay around. The open house is still full.
Okay.
So I'm planning to stick around. If anybody wants to talk to me one-on-one, I'd be happy to
All
do
right,
so.
let's do it that way. Oh, go ahead.
Yeah, this is
Stand up.
Oh,
Yeah, carry.
yeah, this is really fascinating work, and yeah, this is more of a comment, but yeah, we're thinking about the nested arrays, how they are implemented, at least in our APL, is the pointers to another flat array. So yeah, that's and with that technique, there's an overhead when you create a huge nested matrices. So modern like high-performance APL actually tends to avoid such a nested arrays and keep things flat.
Yeah, I can imagine. Very, very powerful, but I imagine they can get you in a lot of trouble.
Yeah, there's overhead if you have a lot of them.
The question is regarding APL and whether it was ever trying to compete with the spreadsheets. I think it was around the same time that the spreadsheets appeared like as a killer app.
Did APL compete with spreadsheets?
Not trying to attempt.
Not in my experience, no. Probably you could implement a spreadsheet fairly easily in APL. At least some of the simpler parts of it.
Minor technical question. So you mentioned something about approximate comparison. Was it only the absolute differences that you could specify, or you could specify, let's say, if it's within like 1 part per billion?
Yes, I didn't show that on the slide, but
So it's
you
possible.
could assign a value to that. So I assigned 0 to say that there's no tolerance, but you could just make it, increase the range or decrease the range of how one constitutes equal.
So it could do the relative and absolute differences.
If you wanted absolute, it would have to be, you'd have to set CT to 0. I mean, a difference, minus is different, it's just going to be minus. But it was the concept of equality, and there's all kinds of nuances of that I hope that I don't have to get into on camera at least.
I'm just trying to like
What constitutes equal.
explain it to my students, like this is how the serious people would have done it. Like anytime you, let's say, compare two floating point numbers, this is what you should do, this is what we do, compared to the like 1 in a million, let's say, but there are other ways to do it properly. So
Yeah, it's an interesting concept. The details escape me all this time later. If Trevor ever finds the source code, maybe I can answer some of those questions. But I know the quad CT value was applied across the board, behind the scenes. It was just something that happened magically, and for the most part, it worked. I don't think I ever changed the value, the default value. Sorry.
Can you assess towards what was sort of the motivation behind choosing a lot of singular Greek characters to represent small operations, as compared to, let's say, in English we can have like a very short phrase, 3 or 4 characters all language that would be more compatible with STP for people.
Okay, so the question is why the cryptic characters? I can't really answer that. I think Ken Iverson has papers out there that probably talks about that. The idea was to make it extremely compact, single character. Why he chose Greek, I guess because Greek is throughout mathematics, and some of the symbols we use in mathematics are Greek, so he just kind of extended the set.
I can speak to that.
Yeah.
Iverson was a mathematician by training, so he naturally great in that fashion. We have a reprint of his original programming language paper over on the table over there, along with other early published works by Iverson. So you could maybe glance through those. You might find, I'm sure he actually speaks to that issue.
Yeah, I did see it quite a bit, so for sure we'll visit that.
Josh?
Sort of comment on that. I also imagine the symbols are useful when you're writing like really long one-line programs. Right? Like.
Yeah, I think some later versions of APL did introduce English letter function names and cryptic things like that. But yeah, like Josh says, if you're trying to make a one-liner, then you want to minimize the number of characters.
Well, you can give the face names in APL if you want to write it in more English style. So that's the APL scribble. Those displayed here aren't necessarily representative of real life APL programs. Yeah, so you can enrich it with English and comments if you wish and often you want to. And I did have a question.
It's sort of supported. He wrote a paper even before that's called Notation as a Tool of Thought. It's kind of like abstraction collapsing an entire series of operations into a symbol. So that represents the idea itself. And then as the ideas keep concatenating, you can do a whole lot. Very little. Notation as a tool of thought is like one of his earliest writing ideas before he did. So I suggest that.
That's really interesting. Thank you.
What did you work on after APL?
Immediately after APL, I think I moved to Wattfile, which how many people have heard of Wattfile? I know Jim has. He's worked on it. Yeah, so I did Wattfile for a whole bunch of years, and funny story was by then Wattcom was down on Phillip Street, and the last project we did at Wattfile was porting into the Mac, and the expert on Mac was in the computer systems group, Carl Duran, so I actually came here for 2 years and worked here while I was porting Wattfile to the Mac, trying to disprove the theory you could not port a command-driven language to a graphical system like Mac. Anyway, at the end of that, I discovered that Wattcom had completely forgotten about Wattfile and the microlanguages and everything had gone off in the C compiler direction. And so I walked back and pushed my computer aside and went down and started working on the C++ class libraries. And then after that, Wattcom SQL became the next big thing, the database server, and that was the remainder of my career.
Yeah.
What did you decide for 0 divided 0?
0 divided by 0. Well, let's find out. Well,
Is it a reboot time?
Well, it's an interesting question because while I was researching this and refreshing my memory, I came across the definition of 0 divided by 0, which surprised me because I didn't remember that if it doesn't explode, it is 1 by definition. For good or bad, it's 1.
One more thing to check if there's a quantitative available.
What did?
Yeah, quad DIV. It controls the behavior of the 0 divided by 0.
You mean the like a system function? Quad
Yeah,
DIV?
system variable. Yeah, quantitative.
I don't recall that one. I'll say
It's
it as-
around in dialog APL. Oh, okay, never mind then. Yeah, it lets you control the behavior. It can be 0 or error as well.
I don't think in ours it's controllable.
Anybody else? All right, well, once again, thank you, Steve. And Steve's here for the rest of the afternoon if you want to engage him in a private conversation.